Okay. On Tuesday's lecture, I think I made the erroneous announcement that homework 11 was due today. You've never seen or received homework 11. It was homework 10, the one that hadn't been collected yet. That's the assignment that's due today. So the first WMS assignment where you are just delineating a watershed. So what I've just handed out to you, homework 11, that'll be due the Tuesday after Thanksgiving break. So you've got about 9 days to finish that one. It's just applying for the same watershed that you used before or a different one if you like. It doesn't matter to me. I just want you to get some practice using the rational method and NSS, which are the two approaches that we did in class on Tuesday, and then also TR-55, which we're going to do today. And then the third and final WMS assignment, which I'll give you on the Tuesday after spring break, is related to curve numbers, the automatic determination of them, and HEC-1 modeling, which is a little bit more robust than TR-55. So any questions about the announcements? All right, so what we're going to do is we're going to do TR-55 activity from the beginning. And so I'm not going to have anything loaded. I'm just going to, if you want to follow along, find Charleston. We'll identify this outlet, try and make sure that we've got the project area set. I don't recall how much progress we made on the TR-55 assignment last time. I don't think we got very far, if at all. So starting with the hydrologic modeling wizard, just because I like the reminder it gives to establish a file name, I'm going to call this TR-55. You got to click Save in order for it to actually create that file number, a file name. Click Next, and then make sure that we're in Zone 17. It shouldn't change. Once you set that, it'll stay on the most recent version. And then for project boundary, define. And if your internet is connected, then what it'll do is, let me switch this, 38, 82, jump to location. Oh, negative 82, right? So I think that puts me in a desert somewhere. That's more like it. All right, we're in West Virginia. I recognize some of these names. Browse up a little bit. All right, so we are looking for Charleston, and it's where the interstate branches. So you can see on the screen there, we'll get the entire watershed that we need, but we could actually, let's see if we can zoom in a little bit more. You can see the branch that I'm wanting to delineate. You begin to see the ridge lines and the streams the more you look at these aerial maps. I think we can zoom in a bit further, and doing that, the advantage is that then everything downloads and delineates faster. Oh, this is pushing it, but I'm going to, Bigley Avenue. Bigley, that's funny. All right, so has everybody got this? And once you click OK, it'll set the 4 coordinates that are the edges, the corners of that. And you may need to, there's this weird bug where sometimes you have to click back down here in the taskbar to get it to bring up the wizard once you do something. But you'll notice that the coordinates are specified, so I'll click Next. And I'm going to use web services to get the DEM, which is the elevation model that allows me to automatically set up the ridge lines. So click Next. The only thing I'm going to need for this one is just the United States elevation data 10-meter resolution. Click Download from Web. Hopefully it should be pretty quick because it's a relatively small area and it's loaded in the background there. Okay. And click Next. We'll want to compute Topaz. Now, just as a reminder, each one of the steps in this wizard has a corresponding menu item across the top. So once you get to be like an 8-hour and 1-day type of an expert, then you won't need to use the wizard anymore. You'll just know where the buttons are or how to access tools through the menu. But this is a nice linear reminder of where things are. So click Topaz. And what it's doing in Topaz, remember, is each cell is being compared in elevation to the cells that surround it, so that a little arrow is going to be assigned to each cell, which indicates where's the lowest elevation adjacent to that cell. And that tells you where the water would flow if a raindrop drops into a certain area. like the direction of flow for the entire raster. So normal program termination means it did that comparison, and then what we've got drawn in the background is these blue lines that identify where a stream is going to form. And depending on what I set for the threshold, if I say I want 10 acres to be upstream, these blue lines are going to grow. There's going to be more of them because there has to be a minimum area upstream before this flow accumulation line is drawn. And so that's just a display option that I can change as I like. Okay. So let me close it for now, and I'm going to bring up a map in the background because I want to have the outlet set right before the interstate. So the way we can put a map in the background is if you do get online maps. So it's got this yellow plus and a couple of multicolored polygons there. So get online maps, and let's do the world street map, and then it's going to show me where the interstate is. You can see it's added here under GIS data an image that it's streaming. And so now we see this was the flat area. We could tell from the contour lines that this was, we're out of the main watershed, but I want to make sure that I put my outlet before the freeway. So I'm just going to drop my outlet on the northern side of the freeway there. If I go back to the wizard, then choose outlet locations. You can create outlet point and then move this out of the way and drop the outlet. Another way to do that is switch modules over into the drainage module. Then here is the create outlet point. You got to be careful with where you click because deleting outlets is annoying. Sometimes you have to just start over from scratch rather than trying to delete the outlet. You just uninstall the whole program, throw away a computer, buy a new machine. It'd be easier than deleting an outlet sometimes. All right, so click in the right spot, and then under DEM, you can do Delineate Basins wizard, or if you're still working through this Hydrologic Modeling wizard, there's the Delineate Watershed button once you've got the outlet set. Okay, so we've got a watershed. Now, I'm going to pause the recording and make sure that everybody's up to this point, and then we'll jump into the new stuff, the TR-55 specific material. Okay, so we've got our watershed delineated, and so go into the Hydrologic Modeling module here, this one, and then switch the drop-down box to TR-55. That's, there's a lot of different models that we can use. Let's use TR-55, and then to bring up the dialog box, do select Basin, and double-click on the Basin icon. All right, and it brings up the TR-55 dialog box. Right now, there's a lot of stuff that hasn't been defined yet for this watershed. Each one of these rows indicates some information that either it can try and get off of the underlying GIS data if you've got some loaded, or you can just manually type it in. So for instance, it knows the area of the watershed, but it doesn't know, see it's got the drainage area, 1.5 square miles. But it doesn't know the time of concentration. So let's do the time of concentration based on the basin data. And we'll do lag time, so compute lag time, and then go down here to the SCS method. We're within the range of the largest watershed you can have for the SCS method. The upper limit is about 19 square miles, and so we're well within that upper range. Now, whether the SCS method is any good for a watershed that's this steep is a totally different story, and the research I've done in the past kind of suggests that it's not, but until we make a correction for it, we'll just do the best we can. Now, it's remembering the curve number from the last time that I put something in manually. This curve number is not computed based on anything in the background. So here in the steps it says, let's assume that the curve number in this area is 68. And that's actually pretty close to the typical curve number for watersheds in Kanawha County when you look at the majority of the watershed being undeveloped, and for the soil type distribution that's common out there, mostly soil type C. Okay, so when you choose 68, then it's going to calculate the lag time is 0.66 hours roughly, should be about that. And then it takes that lag time and turns it into a time of concentration, because a time of concentration is just 5/3 of the lag time. There's a constant relationship between the two. Okay, so it wants us to input a rainfall depth, and let's use the precipitation frequency data server. We'll just pop over to that website real quick and find out what we should use for the 25-year rainfall depth. So here it is. We'll choose West Virginia and drag the cursor to the Charleston area. Zoom in a bit to make sure we've got it roughly in our watershed. Okay, so it's north of the freeway but west of where there's that branch. And we want to have the rainfall depth, and what we need to do is match it to the time of concentration that it calculated. So here it's saying 1.1 hour time of concentration, and this is asking for the rainfall depth, not the intensity. So when you're going to the precipitation frequency server, make sure that you've got it set here on depth and not intensity. So we're looking for, like, what's the rainfall depth for a 25-year storm, 1.1 hours. So we could do a linear interpolation. You know, we'd get 2.14 inches of depth in an hour, or in 2 hours, 2.48. So maybe we could be, well, let's say 2.2, rather than taking the time to do the linear interpolation. Just for purposes of illustration, let's use a rainfall depth of 2.2 inches. All right. Now, we've got a curve number already specified. There's no ponds and swamps in this watershed, so we'll leave that set to 0. Anybody remember what we should say for rainfall distribution? Type 2, and that's just based on where we're at in the United States. We're in a type 2 region. It's calculated the peak discharge here. So it's saying that we should expect to see 80 CFS, 80.9 CFS, based on the characteristics that we put in here. And if we click compute, then it'll generate the hydrograph. And once we close this dialog box, if we want, we can open up the hydrograph. And remember, you may be wondering, why is there so much time before anything happens? You know, like time 0, and then suddenly we've got the peak. The type 2 distribution makes some assumptions about, in a 24-hour period, when the precipitation occurs. And so that's what it's doing there. Now, any questions about TR-55? Mm-hmm. Yeah. Mm-hmm. It's because they have really flashy conditions with watersheds that are extremely steep and arid. It's kind of just because they've got unique hydrology characteristics there, and they've taken the time to classify it, and most other places haven't. All right. All right, so the 24-hour rainfall depth, 4.16. If we increase the rainfall amount, I want to point out that once you compute the hydrograph again, it doesn't delete the old one. The old one's still there, so you can do comparisons if you like. So here was our first hydrograph. Here's the next one. Okay, so TR-55 is pretty easy. Any questions about what we've done here? All right. Well, good. Let's move on now to calculating the actual curve numbers. Now, I've put a text file in the WMS folder of MU Online. You'll need to download that text file for what we're going to do next. So go online, MU Online, and there's only two things in the WMS folder, and one of them is that text file that we're going to use. It has the land use and soil type data. So it's this land use table file. And you'll need to, rather than just clicking on the link, I think you're going to have to right-click Save As. So Save Link As, because the browser would automatically just try and display it since it's a .txt. So right-click on it, Save As, and then just put it to a location that you're going to be able to find later. Okay, we're moving further east, and we're going to be working in Morgantown next. Yeah, good. I needed to hear some booing and all that sort of boo, yeah. All right, so once you get that land table file downloaded, start a new WMS session. You can save this one if you want to come back to it. I guess that's always a good idea. Save the project before you begin a new one. And so let's begin the wizard. Save a new file name. This one's going to be Morgantown. That's what I'll call it. Click Save. Okay, so we need to define a new project boundary and browse over here towards Morgantown. There we go. Let me show you a picture of the watershed that we're doing so that you have an idea of how close to zoom in. Here's the watershed that we're going to be delineating. And so a nice way to get a perspective of things when you're just looking at a contour map is look for the river. Like look for the shape of the river and make sure that you've got these same bends in your window view so that we're going to get the entire watershed area. I'll leave that up for a minute so that you can browse to the appropriate spot and define your project bounds. Some of the bullet points have evolved a little bit compared to what I've got on the handout. You'll see that in just a minute. We don't have to load the land use manually anymore. We've got a different way to do that, fortunately. All right, so let's see. We want to have our watershed is going to include, we've got rivers on both sides. Here's one river, here's another. Okay, I think we've got the watershed. If you've got this same view, then I think we'll be able to get the entire thing. So click OK. We've got those project boundaries defined. Now, web services, but this time we're going to get more. Till now, all you've gotten was the elevation data. We also want to get the NLCD, National Land Cover Database. We've talked about that before. And we're also going to get the StatsGo and the SurGo, just to look at and compare the high-resolution data set for the soil type in the area and the lower resolution soil type. So 4 things we're going to click: the elevation, land cover, and 2 of the soil types, and then download data. It's asking about the cell size because this is where it's offering to downsample the resolution of the DEM file because it's starting to get a little bit big. I'm just going to tell it stick with the original resolution of 10 meter. I don't want it to smooth and reinterpolate the data, so I'll keep it at 10. .30-meter resolution is what it uses for the land cover database. And then the soil type, it doesn't ask for the resolution because it's not a raster. It's a shapefile where it's just a series of curves and lines that are defined in the shapefile, and so it's not ever going to have to like reinterpolate a bitmap in order to generate the data we want to see. Take a moment to read it in. Those shapefiles are large, and sometimes WMS is a little bit clunky and it's conservative. It doesn't want to accidentally forget to download the right soil type data, and so it gets everything in, even in the kind of close. And so if we look at what it got, okay, so let's turn off these two. Here is the soil type, the low resolution soil type data. And you can see that within our area of interest, there's not a lot of resolution. You know, we're going to have, once we delineate the watershed, we'd only have 2 soil classifications if we use the low resolution soil data. But we're not going to use that. We're going to use the high resolution soil data, which is here. Lots of different polygons that are based on that method of extrapolation and looking at ridge lines and looking at where the streams are. And so we've talked about that before and how they'll maybe take a couple of field samples, and then any place that has similar geographic characteristics, it'll assign the same soil type that it found in one spot to many other locations that are similar. But here, this button, the frame button, will zoom you all the way out to however much data is visible. So if you click frame, you'll see that it went and got a big soil map that we don't need because our area of interest is not here. So anytime you see some GIS data you don't need, you can just right-click and delete, and it'll remove it from the project entirely. And I'll do the same thing with this low resolution soil data that I don't want anymore. Just right-click, delete, and it's gone. You may want to save just to provide some insurance in case the program crashes. Okay, now let's leave the soil data off because it's kind of hard to see what's going on when you've got so many things displayed on top of each other, and we still need to delineate the watershed. So we need to run Topaz, identify the outlet, delineate the watershed before we can go any further. So I can either go into the modeling wizard and do those things, or you can go into the drainage module, DEM, compute flow direction, that's Topaz. So it's going to do Topaz. It's running. This is kind of a bigger DEM, so it may take a couple of seconds for it to complete. There it goes, 7 seconds. And the streams are starting to form here. The watershed that we're interested in, I think the outlet is going to be just before it dumps into the main river here. So we're interested in this watershed, which has a stem here. So let's drop our outlet point in this region, and then under DEM, delineate this. It's doing its thinking. Calculating the flow distance. All right, so about 5,000 acres. Let's have that change, instead of showing acres, let's take a look at what that is in square miles. In the display options is where you can change it. Change units from acres to square miles. Oh, it didn't do that, did it? We don't want the land use grid on. I think I may have to redelineate if I want it to update the units there. So let's try that again. Delineate basins. Are your laptops a little bit slow for this? It's a big watershed, not as big as the other one that we had. Okay, about 8 square miles, so it's not too overly big. Let me pause the recording, give everybody a chance to catch up. Hold on to your wizard hats, it's about to get tricky, all right? So you'll notice that right now we have a land use grid, and if you click that, these colors correspond to, let me turn off the DEM. The colors correspond to different types of land use, and so the yellow shaded areas are more urbanized, the black areas are just mostly vegetation. Each one of these colors corresponds to a number that is assigned a land use. And you remember that you downloaded a table. So that table that you downloaded, the curve number table, so each one of those colors represents one of these numbers. Okay. We need to create a new coverage. Right now we've just got this drainage coverage, so right-click on the coverage and do New Coverage, and what coverage type we need is a soil type coverage. Because right now we've just got the soil type in the GIS data and we want to put it into its own coverage. All right, so now we've got a soil type coverage, a land use grid, and our drainage coverage. Turn off the grid, turn on this GIS data, and what we're going to do is we're going to select the polygons that are in the same vicinity as our watershed. So here's our watershed. I've zoomed in, I fit it to the window so that the watershed is here, and I only want to select the polygons that are going to be relevant in our watershed, just to try and reduce the size of what's in this soil type coverage. And so once you click on the GIS data, you'll notice here we've got some select feature tools, and we're going to just click in one end of the window and drag. And so it's going to select all of the polygons that are inside of this watershed or go across the boundary. Okay, so once you've got them selected, then we're going to do mapping, shapes to feature objects. So we're going to take what right now, which are just a bunch of GIS lines, and we're going to tell the program that actually those lines represent something as far as hydrologic modeling goes. That a feature object is something that the program can look at to calculate parameters like curve number. So map the shapes to feature objects. And so we're going to put it into the soil type coverage. And oh, I forgot something, guys. All right, right-click, join NRCS data, and then we'll do that mapping. Join NRCS data is basically the one attribute that's most important for us is the hydrologic soil group. Remember A, B, C, D, and it has to go into a table that it downloaded to get those values before we map it to the coverage. So join NRCS data, and what we want to do is join the hydrologic soil group. If for whatever reason one of the polygons doesn't have a value, you can have it fill in any place that's a blank with the most dominant soil group that it's found, which is D. Now most of these, even if we didn't tell it to fill in the blank values, we'd still be fine, but just to be safe, it can assume that any polygon that doesn't have a hydrologic soil group assigned is going to be the same as most of the rest, which is D. So you click OK, and so now what it's done is it's joined these shapes to some underlying data. And now we're going to do this mapping shapes to feature objects. So we're going to put them in the soil type coverage that we just created. And the source of that was that shape file. Next, and we're going to make sure that among the mapping it's going to do is the hydrologic soil group. So right now, from the GIS file, that field is called HYDGRP, and WMS knows that that's supposed to be the SCS soil type. And so this SCS soil type is what's important for us to be able to calculate the curve numbers. So we confirm visually that it's making that mapping, and it is, so that's good. We can click Next and then Finish. And now if you turn off the GIS data, we still have these relevant soil type polygons in the soil type coverage. So that's where they need to be. Any questions so far? Everybody get those polygons in the coverage? You're doing, looks like Topaz. All right, well, let me pause the recording because we are not dying for time for once. We actually have time to do this the right way. Let me pause this. All right. So here's what we're going to do now. We're going to use that table to calculate the curve number. Go into the Hydrologic Modeling module. Under Calculators, we're going to compute GIS attributes. And then we want it to compute the SCS curve number, and it's going to use the soil type coverage for determining soil type, and it's going to use the grid for determining land use, and then it needs to have a table that it will read to know the curve number for each of the soil groups. So that's where we're going to import the table that you got from MU Online. So hopefully you save that in a location that you can find. That curve number text file, and you'll notice now it's got a curve number for each of the land uses that we have. And once you click OK, it's going to just basically, the calculations are done, and it needs to know where to save the report. It's going to open up the report automatically in Notepad, and then here it is. It's done a weighted average based on all the soil types and land uses inside of our watershed. And you can see that there's a lot of different combinations. Most of these are relatively small fractions of the watershed area. The biggest component, most of it's deciduous forest, 1.8 square miles. That seems like there's a lot of soil type A deciduous forest with a curve number of 30 for those sections, and so that's a really low curve number. But there's also some developed high-intensity areas with soil type D with a curve number of 95. So it's doing this weighted average, and so the weighted overall watershed curve number is 67. And after it does that calculation, you can save this report in a folder someplace if you want to print it off, or use it as the justification for why the curve number is the way it is. But it's already put that curve number into the drainage coverage. If you go back to drainage, we can turn off the soil type in the background. We don't need to see all those shapes. It just makes it a little bit visually distracting. We can switch it off. And so if you go back over here to the Hydrologic Modeling module, the default assumption is that you're going to be setting up a HEC-1 model. And so if you double-click on the basin and bring up the parameters, here under loss method, it's got the curve number that it calculated, already specified. It's any place it can put in a calculated field, it will. And so under the unit hydrograph method, for instance, if we want to calculate the lag time, we can do it based on the basin data. And here we've seen this field several times before. Scroll down to the SCS method, and this time instead of entering a curve number, it's using the curve number that it calculated just now when it looked at the combination of the land use and the soil type. So it's that 67.3. It's got our watershed slope that it determined from the DEM, the digital elevation module, the watershed length. It basically looked at all of the flow path routes in the entire watershed and found the one that was the longest. That's how it found the watershed length. And so here's our lag time, 2.04 hours. We also need to specify some precipitation to do a HEC-1 model. Does everybody have these HEC-1 parameters up? I'm sorry, you're having a bad computer day. Oh, I'm sorry. Okay, so if you click on precipitation, let's do a basin average so that everywhere in our basin has the same average precipitation. You can, if you have gauge data, set up gauge locations and where they're at and what the measured depth was, and it'll use the Thiessen method or the isohydral, and it'll calculate an average for you based on that. Let's just do this basin average and get precip from web. It's going to pull the precipitation frequency data server, and it says, all right, we want to have, let's look at, in this instance, a 10-year storm. The latitude and longitude it has from our project area location, a 24-hour storm duration, get data. So the mean, the upper, and the lower. That's the 95% confidence interval that it reports on the website. It'll just use the mean value, about 3.46. So here's our precipitation for a 24-hour duration storm, and that was a 10-year storm. So you click OK. Oh, define series. We also need to tell it it's a type 2 storm. So under define series, under selected curve is where you tell it the temporal distribution of the rainfall. Remember, temporal distribution is basically when over time is the depth actually occurring. And we have a type 2 24-hour storm. The 24-hour storm depth based on what we just looked up, and type 2 because we're in West Virginia. And so here's, when the precipitation occurs. Here we have our peak intensity zone halfway through the day. So click OK. And everything's specified at this point. All the main things we need to do are precipitation, loss method, and unit hydrograph method. We're not going to include snow melt in this analysis, and the basin data and output control, that's not anything that we need to adjust. In all of these fields that we're entering, what it basically does is it's assembling a text file that's got a very specific formatting requirement. You look here in this window, if you scroll down through it, it's got a bunch of columns of data. These numbers that I'm scrolling through here, this is the precipitation, like the how much versus what time of the precipitation, but it's got other things as well, like the precipitation depth. PB is the abbreviation that the program uses for the precipitation depth. BA is the basin area in square miles. Each one of these abbreviations tells it, like for instance, the curve number, the time of concentration, and so on. So what the program's going to do is, instead of just like one pulse of rainfall, it's going to do a calculation for each one of these steps. It's going to say, when you have this much rainfall, 0.001 inches, what happens to the basin? And so it's going to start routing the water through there, and then it's going to say, all right, I already know about this rainfall pulse 15 minutes ago. Now what happens with this next amount of rainfall? And so the HEC-1 simulation, if we go into the job control, let's go into HEC-1 job control. It will do 100 different time step calculations, unless I say that I want 150. And 15-minute computational time interval is the default, and that's a good value to leave it on. If you go anything smaller than that, there are these strange program artifacts where you think you'd be getting more resolution, but actually it kind of messes up the peak flows a little bit. So just leave the computational interval at 15 minutes. But it's going to do 150 time steps, and once you click HEC-1 run simulation, you have to specify where you want the files to go. And sometimes you can get an error message if you have like a subfolder within a subfolder within a subfolder within a subfolder. Like if it's too many subfolders deep in a program directory, sometimes it won't run. So you'll notice here I've just got it C hard drive, the temporary folder, WMS temp, and then untitled. I could call this Morgantown if I wanted to, the output file. You can open up this output file. It's just a text. So here's Morgantown. And click OK. And it went through 150 iterations that quickly, and it will create a hydrograph of the outlet. So here's the hydrograph of what's going on. It's telling me the peak flow. And if you want to get this data, this hydrograph data, you can export it by right-clicking on the hydrograph and then do export/print. Well, I guess before I do that, I want to make sure everybody's got a hydrograph. It's probably you didn't change it from 100 to 150 in the job control, and that's fine. I mean, you can still see the peak. Yeah, keep doing the same thing over and over again. Go into, let's see, you're in the hydrologic modeling module already? Mm-hmm. Hold on a second. Do you have the select hydrograph button?
Yeah, it's on now.
What about if we go into hydrographs list?
I didn't select it. But I don't know.
Selected.
All right, did you run the thing where it calculates curve number for you? I think so.
I don't know. Maybe if you had a mouse, I don't know. Wasn't the issue last time like it wasn't, I mean like it wasn't doing a left click or something?
Yeah, it wouldn't do the left click to move anything.
Yeah. I'm sorry. It's. Uh-huh. Mm-hmm. Yeah.
Now it's got 2 on here.
Yeah.
But I think it was this. Yeah.
Yeah.
This was the original. What have I done there to where
It's probably just 30. I'm guessing that if you go back into the job control, it's probably just doing 30 ordinance, is my guess.
Well, I went and changed it because I thought it was supposed to be 150.
Do 15 minutes.
Oh, 15.
Yeah.
Okay. And then there should be 300.
150 would be plenty. Yeah. You got a hydrograph?
To be underneath the basin tool to double click the basin.
Okay, so that's fine. Go into the unit hydrograph method. All right, you've got a lag time. That's fine. Okay. And go into precipitation. All right, do define series. Yeah, you've got it. Okay, that's all you should need. No, it's type 2. Type 2, 24 hour. I'll click. Okay. Okay. Done. And now HEC-1, look at the job control just to make sure that we've got, okay, that's fine. And do hydrographs delete the previous? Delete all, okay. Now HEC-1, run simulation. Close. You got hydrographs. Do you got a hydrograph? All right.
My peak flow is a lot lower than yours. That's something I should be concerned about.
My guess is maybe you didn't use the type 2 distribution. Let's see. That's right. Let's see what we got here. All right. Precipitation. I think didn't I do, oh, you just got it from the web, right? Yeah, yeah. Okay, so you're doing a 50-year. Didn't I do? We've just been doing other stuff. Yeah, I thought I did a 10-year.
Yeah.
No, that's all right. You don't have to apologize. That's what you get for following directions, right? All right, so we're using, 3.46. I think that's the rainfall depth that I used, so that's probably why you're seeing a different one. So now what you can do is go and delete all hydrographs and then run it again. Okay. And so I think that'll probably be closer to the value that I've got. Is it? 800? Yeah, roughly, right? The difference is probably just where you put the outlet, slightly different. Yeah. Okay, so once you get to the point where you've got a hydrograph, right-click on it, and we're going to do export/print. And instead of exporting an image, if we want the actual underlying data, then you do text/data, and you choose a file location that you know you'll be able to find again. And so I'm going to call this Morgantown text.txt. I'll have to import it into Microsoft Excel. Now when you click export, that's not the end of the story. It's going to ask you, like, what do you want in the columns and what do you want in the rows? And so what we're going to do is a table, but we want points/subsets, if I remember correctly. So now click export, and then let's open up and see if what we got. Here's the Morgantown text.txt. So I'm going to start Excel and try and import that text file that I just created. And with any luck, let's browse to that location. You're going to have to change it to include all files. Here's that Morgantown text that we want to bring in. It is delimited with commas. So if you do comma delimitation, next, finish. Okay, so it's got time versus flow rate. So this first column here is, it puts a bunch of nonsense at the top, but you can just look at it and kind of know that this is time in minutes, and then this is runoff in cubic feet per second. So that we could make our own presentation-ready graphics by inserting an XY, select the data. Our X value is going to be time, and our Y value is going to be this runoff. Okay, so that hydrograph looks the same as what we just saw, but now it's in such a format that I could add axis titles and make all the adjustments that's going to turn this into what I could paste into a report. Some axis titles in here. Time in minutes. Here is the runoff. CFS. This is the 10-year storm, right? No, it's not sarcastic. This is next level stuff I'm going to show you. It's so that if you wanted to do stochastic modeling, or maybe you've heard of a Monte Carlo simulation. Looks like Lance just about threw up when I said that. Did you just gag when I said a Monte Carlo simulation? I think I struck a nerve. All right, so delete your previous hydrographs. Hydrographs, delete all. All right, go into HEC-1, Stochastic Modeling. What you can do is, if you're not exactly sure what the curve number is, but you think it's maybe, we had it calculate and it was said 68. But there's still some uncertainty there. Those measurements could be wrong. And so if you wanted to define your confidence interval and say, like, well, what's the range of possibility of runoffs if maybe my curve number is as low as 63 and as high as 72. Okay, so go back and open up the HEC-1 parameters, and under loss method, instead of curve number 67, we're going to say that the curve number is -1. And -1 is just a flag that if it sees -1, it knows to look somewhere else for the curve number. So we're going to be defining the curve number in another spot. Now, it's still using the same lag time, though. So the lag time is not going to be updated a bunch of times. You know, we calculated the lag time here under the unit hydrograph method, and so it's going to stay at 2 hours. Now, in reality, if you have a different curve number, you're going to have a different lag time. So this isn't like 100% slick and where it's updating every possible consequence of a different curve number, but it is going to change the loss method. So we've got this -1 set for the loss method. Okay, done. And now go into HEC-1 stochastic modeling. And we're going to do a Monte Carlo, just for sake of time. Let's not do 100 simulations. Let's do 15. And define the stochastic model, add a variable, and we're going to, you see how it says key -1? So it says you should put a -1 in your curve number, and then our starting point, what did we say? It was going to be from 63 to a maximum of, let's say, 73. We know that it's somewhere in the range there. So what it's done now, if you scroll sideways, it's got 15 runs, and all of these values that it's choosing for the curve number, those are randomly generated. It's within the range of 63 to 73, but it has a normal distribution, you know, like a bell curve. And so when it generated those, it followed, you know, like if we took the average of these values, the average is going to be in the middle of the 63 to 73 range, so the average should be 68. Okay, so it's going to do 10 runs, and for each one of those runs, it's going to have a different curve number. So click OK, and then run stochastic model. OK. Oh, I did a bad thing. I think it was buried too deep. Let me, okay, stochastic modeling. I'm going to put the, let's see. Yeah. Yeah, this minimum? Oh, yeah, good question. It might be start, minimum, and max. Oh, now that I think I should have done 63 for the minimum rather than 63 for the start. The way I usually use this is you can set this to be whatever you want. You don't have to use the normal distribution. You can override it. So we could do, like, what if there's a 60, 65, and so on. So I'm not usually using the normal distribution. I'm usually overriding it manually. But I think you're right that it is the minimum. So that's still, all right, so HEC-1, run stochastic model. Error. I think I need to save my HEC-1 file not quite as deep. So
Why make minimum 63 and make the runs below 63?
I wouldn't. It's just to show you how to do the stochastic modeling. There's really no significance to the actual run values here. It's just to show you that when it executes the, let's put this base file name in here. One last try, and if it doesn't work, we'll have to pick up on stochastic modeling after the break. Hey, it worked. All right, so see what it's, I needed to save, it was in the programs folder, which had that error of it was too many subfolders deep. So it's executing model after model after model now. It's just going to do 15 of them, 12, 13, 14, 15, and it's done. And then it will load in my hydrograph here is the spectrum of runoffs, the range that you'd expect to see if the curve number started, I don't remember, did we start at 60 and go up to 72? Anyways, for each one of those different curve numbers, it's generated a different hydrograph. And if I exported this, then it would create an Excel file that had a column for each one of those, two columns, time versus runoff for each one of those runs. So there's two things that you can do stochastically, the curve number and the precipitation depth, because those are the two factors that have the most uncertainty surrounding them. So if you wanted to have a two-factor stochastic model, you could say I've got uncertainty in my runoff depth, and so I'm going to have like a normal distribution in runoff and a normal distribution in curve number. And you could do 100 runs, 200 runs, and just see like what's the range of possibilities. So that's just for your information. There's nothing HEC-1 related in the homework that's due on Tuesday. The homework that's due on Tuesday, I think, finishes with TR-55. So we've made a little bit more progress than you're going to need to know for the homework. But hope you have a great break. If you've got questions over the break, send me an email and I'll do my best to respond. Hopefully the computer issues heal themselves or you can overcome them. But I'll see you a week from Tuesday.